Okay, so we're talking about transport layer, right? Okay, and if my memory serves me right, we got to this point. We started to talk about some of the functions that are implemented in transport layer. So just to remind you, transport layer is about end-to-end reliability. And so when we look at all the discussions, you should always be looking at where is end-to-end reliability. So do you remember this? We ended at this function, multiplexing and demultiplexing. So who can tell me where is the end-to-end reliability here? Do you know? No? It's okay. How about you? This lady here? Hi. Do you know where end-to-end reliability is? What's your name?
Melina.
Huh?
Melina.
Melina, do you know? End-to-end reliability. Is it? And what was your name? Huh? Janice? Shanice. Okay. Shanice and Melina. Any ideas? Where is end-to-end reliability? So how about, is this related to end-to-end reliability? So multiplexing and demultiplexing was a function implemented at the transport layer. And the question is it related to end-to-end reliability? The reason we ask this question is I've kind of asked you to think about what the main function of transport layer is. And we have decided it's end-to-end reliability. So is this related to end-to-end reliability? So it's yes or no? What's your guess? Yes. How about Melina? Yes. Okay, how about the rest of you? Yes or no? Okay, how about it? Who says yes? Raise your hand. Who says no? Okay, do you want to share? Okay, so let me talk to the yeses. So you two said yes. Do you want to share why, or you'd rather not? Why is this related to end-to-end reliability? Melina or Shanice? It's okay, you can say I don't know. Okay, good. So it's just a guess. Do you know, Melina? Huh? Because it's in the transport layer. Okay, so that's a good guess. This gentleman here, you said yes or no? You said yes, right?
Yeah.
What's your name?
Frederick.
Frederick. You said yes. Tell me why.
It was a yes.
It was a guess. Okay. The gentleman in the red shirt said no. Tell me why. What's your name? Huh? Huh? Yeah. So no, yeah. So why did you say this is not related to reliability? That's what you said, right? You raised your hand to know? Yeah. What's your name? Thomas. Tell me why you think it's not part of end-to-end reliability. Okay. Yeah. So the answer is no. Okay. It's not related to end-to-end reliability. I guess if you really wanted to, you could probably construct an argument that it's related, but it's not directly related. And I think because there are no mechanisms in here for reliability, things like error checking or retransmissions, right? In multiplexing and demultiplexing. So this is another. So Melina, you said because it's implemented at the transport layer. That was a good guess. But what we find is that often functions are implemented. They need to be implemented somewhere, right? So this function is clearly necessary. And it needs to be somewhere, okay? And it just happened to be implemented at transport layer, okay? So sometimes the function may not be part of it. So that's why it's helpful to ask the question because it teaches you something, right? So in this case, the multiplexing and demultiplexing is because the point is that it's a process, it's an application, or more specifically, a process that consumes information and generates information. So you need a way to address it because on a specific network interface, you can have multiple processes. So you need a way to address, and you have one network interface, one wire. So multiple processes need to be multiplexed onto the wire, and on the reverse link, they need to be separated or demultiplexed. So that's why this function is there. Okay, and the takeaway message is that we use the port to address the process. Okay? On a network interface, we use the port to address the process in a similar way that we use your name to address you in your household. Everybody in your household has the same postal address, but you each have a different name. Okay? If you had the same name, we'd be in a problem. There'd be a conflict. If there were two Mehuls, we'd have to have Mehul 1 and Mehul 2. We need it to be unique. Okay? So the port address on a network interface, the port address for every process needs to be unique. Okay, and this is done at runtime. When you run a process, the operating system automatically assigns it. Now in your lab, you're going to have to open up a socket, a TCP socket, right? And you're going to, you probably have to assign a port number. Okay, so this is the port number. Okay, now a web browser, you know, for example, runs on port 80. Or a web server, sorry, runs on port 80. The web browser is a random port. Okay? So with that, I think we do as in we finish the discussion on multiplexing and demultiplexing. The only thing to keep in mind is remember this when we talk about NAT, network address translation, because there's a very strong similarity between NAT and multiplexing and demultiplexing. In some sense, NAT is doing multiplexing and demultiplexing at the gateway router. That's the connection. All right, so now we get into things that are related to the main function, and there are two main protocols, TCP and UDP. Because UDP is short, we'll maybe address it and, again, put it to bed. Okay, so UDP is User Datagram Protocol. It's a transport layer protocol that doesn't do much about reliability. Okay, it's there when you don't care about reliability. Providing end-to-end reliability costs you something. You have to pay a price for it. We'll talk about what the price is. But when you don't want to pay that price, you still need a placeholder because the reference stack has a transport layer. You need to provide the interface. It's a good example where you need to provide the interface to the layers above and below, but you can change the functionality inside because of the layering. Okay, so UDP, this is the anatomy of a UDP packet. You still have your source port and destination port. They're always there because multiplexing and demultiplexing is done at transport layer. But then you have two other fields. The next 32 bits, the first 16 bits is a checksum. Next 16 bits is the length of the packet, and then you have your data. This is all that's there in the transport layer. So at the most, what you can do is check if there was an error introduced. Is the checksum, does the checksum match? If checksum doesn't match, you throw away the data. That's all you can do. There's no mechanism for retransmissions. Okay? So that's UDP. All right? So UDP is a very lightweight transport layer protocol. Okay, when do you use UDP? You use UDP when you don't want to pay the price. So what's the price of reliability? The price of reliability is delay, latency. Okay, because you have to do extra things, it slows you down. So when you don't want to be slowed down, you have to use a faster, lightweight protocol called UDP. So for example, DNS, okay, I think on the next slide I touched, so DNS uses UDP, but the price is to build up this connection and to maintain the connection and manage it and provide reliability over this connection, you have to pay a price. Okay, the headers are longer, retransmissions take time, you have to wait for acknowledgements and so on. All that takes time. Okay, so you'll see that when we talk about TCP, there's a price to pay. So who uses UDP? So for example, DNS, right? We saw that on Monday's lecture when we did the Wireshark dissection of the packets. Right? You saw for DNS query, the transport layer protocol was a UDP packet. Right? Do you remember that? Yeah. So okay. In the past, real-time sort of multimedia streaming protocols used UDP. So for example, if you were trying to do video teleconferencing maybe 20 years ago, okay, you would have used UDP. These days, the network has gotten very, very reliable that teleconferencing applications like Skype, WhatsApp, FaceTime, WeChat, all use TCP. Okay, so right? I mean, you all do these kind of calls. Does it almost feel like you're making a voice call? Like if you do a voice chat over WhatsApp, does it feel like a voice call? Or is it pretty bad? Is it pretty bad? Really? I have decent experience with it. Yeah, I mean, you can't like go deep into a like underground metal basement and try to make a WhatsApp call. Is that what you're trying to do? Yeah, of course it depends on your connection. But let's say you do it over Wi-Fi. You make a WhatsApp call over Wi-Fi. Is it still pretty bad? I think you have very high expectations, maybe. Like you want like MP3 quality voice, right? No, I'm just kidding. I have pretty good experience with it. Yeah. What about the rest of you? What about you, Melina? It's okay, right? I mean, like we're still using it. You're not complaining, right? You're not looking for another solution. Whereas like 20 years ago, I was trying to do this. I was in the U.S. My girlfriend was here in Singapore, and we were trying to like communicate. It was so painful. Like I'm running on a Linux box trying to run somebody's beta version of some multimedia streaming protocol, and it was horrible. Okay, pre-Skype days. So I hope you can't figure out my age from that. Anyway, so okay, so that's when we used UDP. But these days, TCP seems to work even for applications that latency matters, like voice and video. We still use TCP. Okay, but DNS still uses UDP. Okay, so we've put multiplexing and demultiplexing to rest. We've put UDP to rest. Okay, UDP will come up a bit later when we talk about congestion control, because we want to look at the so TCP is this kind of sophisticated, reliability-focused protocol. Okay, but what happens when TCP and UDP flows interact? That's when UDP will come back up. Okay, but for the next lecture or two, we're going to focus on TCP and all the mechanisms that it provides for reliability. So what are those mechanisms? So TCP is connection-oriented. Okay, stream of byte service, that's kind of just a fact. But it provides reliable, in-order delivery, which means that packets arrive in, or packets when they're presented back to the application layer are in the correct order. Now, can anybody tell me why would they be out of order? Now, packets are sent in order, right? If you have a stream of packets, 1, 2, 3, 4, 5, you're going to send 1, 2, 3, 4, 5, right? Or are you going to send 5, 4, 3, 2, 1? Like, what is the transmitter going to do? If the correct order is 1, 2, 3, 4, 5, in which order will the sender send the packets? Huh? In that order, right? 1, 2, 3, 4, 5. So the mix-up is not coming at the sender. But I claim that at the receiver, they might be mixed up. You might get 1, 2, 4, 3, 5. Why might that happen? Can anybody tell me? Yeah?
The packets take a different way to get to the receiver.
Okay. So the rest of you, any input? Why? So that's a good idea. I like it, Frederick. Okay. Anyone else have an idea? Okay. Maybe the packets were dropped. Okay. So that's another idea. So packets were dropped, and okay. Thomas? Oh, the same. Okay. Anyone else? Yeah, so there's remember, the internet or packet switch networks or networks that use statistical multiplexing, all the same, are best effort networks. They don't provide guarantees. And because they don't provide guarantees, you can get all these things like packets getting lost and out of order. So what Frederick said is right. There's no guarantee that two packets from the same flow, from the same sender to the same receiver, will take the same path. They might take different paths. And you might have, remember when we talked about sources of delay? Queuing delay. One path might have a router that's more congested than another path, in which case that packet will get delayed. So packets arrive out of order at the receiver, and the transport layer will put it back into order. Okay, that's one of the jobs. So other mechanisms for reliability include checksums to check if there was a corruption in the packet, right? Like did something happen to disturb the contents of the packets? There are acknowledgements, right? Acknowledgement tells the sender the receiver got the packet. There are retransmissions if I don't receive an acknowledgement, and there's sequence numbers to detect losses and to put stuff in order. Okay, all that is there at transport layer. These are some of the mechanisms for giving you end-to-end reliability. Now, two other mechanisms I broke out because they're very important. One is called flow control. Flow control is to make sure that the sender doesn't overwhelm the receiver. Okay, now you talked about flow control in layer 2, am I right? You must have, because that's an issue with hop-to-hop as well. You have to make sure that the one hop, when it transmits to the next hop is not overwhelmed, meaning its buffer is not full. Because you know if you get a full buffer, packet will get dropped. So why should you force a packet drop? No point, right? It's better you back off. It's better you stop transmitting, right? So did you talk about flow control at link layer? Yes or no? Okay, so there's flow control at the transport layer as well. But transport layer is sender not overwhelming the receiver. Congestion control is sender not overwhelming the rest of the network. Okay, you want to make sure you don't cause packet drops along the path as well. Okay, we just break it out because the sender has a virtual communication linked to the receiver. But the sender does not have an explicit communication link to the other nodes. So what we'll see is that for the flow control, there's an explicit mechanism. For congestion control, there's an implicit mechanism. But both are trying to do the same thing, not overwhelm the network. And we'll discuss these especially congestion control, in great detail. Because you have never seen congestion control. You've seen flow control, you haven't seen congestion control. Okay, so do you understand the mechanisms that TCP has for reliability? And we're going to study all of these. That's the next few lectures. Okay? And yeah. Good? Can I go on? All right? Okay, so yeah, so just to motivate, like stuff, let's say take out of computer networking. Like think of you talking on a phone. Like you're on a phone call. Like, hey, what's up, And so you're talking to someone. Now, what's going to happen? When you talk to someone, do you keep quiet? Like somebody's telling you a long story, right? They're like telling you how their prof gave them so much homework and is really asking them to do like projects and homeworks and labs, and it's really not fair. But like, do you keep quiet? What do you say? Like, you don't want to interrupt them, but yeah, you'd be like, yep, gotcha. If you keep silent, it's like, eventually the other side will say, hey, are you listening to me? But it's really funny, right? Because listening doesn't involve talking, and yet when you keep quiet, they say, are you listening? Like, I always find that funny, so humans, slightly irrational. But you want to make sure that the connection is there, that they're understanding what you are saying. In the same way, we can port that same idea to a computer network. The sender doesn't want to just keep sending, hoping and praying that the receiver got everything. Because there are possibilities of corruption and packet loss, right? You want some acknowledgement from the receiver. And so TCP builds, so that's the reason that TCP builds in acknowledgements, right? And then so, for example, if the other person didn't hear, you would just repeat, right? You'd be like, hey, I didn't catch that. And so you'll repeat yourself. In the same way, the sender will resend packets that are lost. Okay? Now, this is not taking into account something called error control coding or channel coding. This is something we study in the communication systems class, which I also teach. So if you're interested, check out EE3131C. Okay? In that class, we talk about channel coding or error correction codes, which are also related to robustness to to errors. But they're more of a physical layer device, or some could argue it can be done at application layer as well. But it's not done in the stack. In fact, though, the CRC check, that checksum, you talked about CRC, right? Actually, the CRC is an error correction code, if you hadn't figured that out. In fact, it's not an error correction code, it's an error detection code, right? The idea is that you introduce redundancy so that the receiver can detect errors, and this is going to blow your mind, you can correct errors. Without knowing the error, you can correct errors. So to me, channel coding is like magic. If you really want to see true magic, you should learn channel coding. Okay? It's like, imagine I send you a bunch of packets without you knowing if there were errors and what the errors are, you can correct them. Sounds like magic, right? Like you read the channel's mind. Yeah. So that's why I think of it as magic. But here, so it turns out that retransmission is actually a very, very simple error correcting code. It's a repetition code. Right? It's the very simplest thing to do. But at the network layer, that's what we do. We retransmit packets. Right? You speak again if the other person didn't hear you. Okay, so in some sense, what TCP does with its acknowledgments is exactly what we do in communication. So this is what I'm trying to kind of motivate here. All right? All right, and then, yeah, so there are acknowledgments. Now the other thing is, if let's say you're talking, and for a long time, you hear the what are you going to think? You're going to think that the connection was dropped, right? Yeah, and so the same thing happens in computer networking. If I don't hear an acknowledgement after a certain amount of time, I'm going to assume the packet was dropped. So, right, it's not that I got told I didn't hear you, I just don't hear anything from you. Yeah, I mean, so I have this experience all the time with my wife. So I'm calling her, and then I'm talking for a while, and then I hear nothing, and then I realize the call got disconnected. Who's experienced this? You're talking, and then you're like, hey, I'm talking to myself. Right, so then I'll call her back and say, I just said the most profound thing, and you missed it. Right, and she'll start laughing because she doesn't think anything I say is profound. So there's timeouts, there's acknowledgments, and retransmissions, which is what, again, I'm trying to draw the analogy between the real world and how we communicate to how we communicate in the computer networking world. And there's a lot of analogies. Okay, so a lot of the things you can actually predict. Now, of course, once you get the basic idea to actually architect it to build a protocol, we slightly deviate from the human world because we're not computers. Right? Computers need rules. We have brains, okay? So, but I think the analogy can work. You can predict almost all of the functions that we do in TCP from how we talk in the real world. Okay, yeah, and we already discussed this a little bit, that the communication is prone to errors, to losses, right, and so on. And so that's why you need reliability. Okay, so things can come out of order, they can be garbled, they can be nonsense, right, and you can actually miss packets. Okay, so you have all of these, and you need to deal with all of this. Okay. Okay, so this is maybe a little bit of a summary, not summary, but a repetition from a few slides ago, but it's worth repeating. So this is about the reliable delivery. We'll look at the flow control and congestion control later, but the basic mechanisms that TCP has for reliable delivery are checksum. So checksum is simply an error detecting code. You call it CRC, cyclic redundancy check. So what is it? It's extra bits you add. Those extra bits are a function of your payload. So you can imagine, right? They will, if you have a certain payload and you have a map, you can think of it as a hash function almost, but it's okay. So it's yeah, but so you have a payload. Your function of your payload are my extra bits, right? Now, if I receive the packet, I look at my payload. I compute what those extra bits should be. If it doesn't match, then I know something went wrong. Because if it did match, it's likely something did not go wrong. Actually, something could have gone wrong in just the right way, right? Correct? Because it really is like a hash function. You can get collisions, right? But it's just like hash functions. You can compute probabilities of collision and so on. So you compute this check. If nothing went wrong, something could have got wrong, but it's very unlikely. So you just assume something didn't go wrong. Now, if the checksum doesn't match, you know something went wrong, for sure. Right? Either in the message, in the payload, or in the checksum itself. Okay? Now, in the stack, there's checksum at many layers, right? The link layer has a checksum, network layer has a checksum, transport layer has a checksum. And one of the questions that I'm going to ask you later, we're not going to do it now, is why are there so many checksums? Why isn't one checksum enough? Something to think about. This also bugged me, right? Like all the questions I ask you are things that bugged me when I learned about them. Why are the checksums at all three layers? But anyway, the checksum is used to detect errors, and the way we usually treat it is if there's an error, I discard the packet. Okay? It's very unfortunate because that's a very suboptimal thing to do. It turns out if you study communication systems, you should not throw it away. Okay? You get some information from it, and you should use it. Okay? The second thing is there are sequence numbers, and the sequence numbers are used to detect missing data as well as put data back in order. So we'll see there's an explicit mechanism of sequence numbers. And then when data is corrupted or lost, there is a mechanism for retransmitting packets. Okay, and just like link layer, because link layer also has retransmissions, right? You called it, what'd you call that algorithm or that general mechanism of retransmission? You had a name for it. Do you remember? You shouldn't forget everything. So think back to link layer. What was the mechanism for retransmission? You give it a name. Starts with an A. Yeah, ARQ, right? Automatic repeat request. And there are many protocols for ARQ. Stop and wait, blah, blah, blah. And you probably ended on sliding window, right? Because sliding window is efficient. Stop and wait is very inefficient. ARQ, sliding window is more efficient. And so this is what TCP uses. It uses a sliding window mechanism. Okay? And so we're going to discuss this in some detail. Okay, so we start off with talking about TCP segments. So this is the beginning of it all. So what happens at the transmitter? We're looking at transport layer. Okay, this is what the transport layer does. Okay, so as I said, TCP creates a stream of bytes service. Okay, so you have essentially, there's a virtual, like kind of virtual byte channel. Okay, so these bytes are going to come across. So let's say, and you can see I've enumerated the bytes, right? So you already see that there's some sequencing that's going on. Okay, so what happens is at the transmitter, I'm going to have a buffer, right? I don't send a byte at a time. I'm going to collect a bunch of bytes. Okay, and I'm going to put it into a segment. Okay, and I'm going to send that segment over. Okay, so sort of that's the basic idea. And what happens is TCP obviously has to wait for the segment to get full. So if my segment is of a certain size, 64 bytes, I have to wait until 64 bytes come in. And when they come in, I send them. So you already see there's a delay because the first byte was ready to be sent. When I generated it, it's ready to be sent. But it's going to have to wait until I get all 64 bytes. So we already see there's a price. I'm not pushing out that first byte immediately. I'm going to wait until I fill up my buffer. And I mean, in the standards, this is called the segment size or maximum segment size, MSS. Okay, and usually you wait for it to be full, but you don't wait forever. right? There's a OS mechanism to timeout, right? So at some point, the OS will just push unfull segment if the time is too long. All right, so, okay, so that's the basic idea. So what does this segment look like? So essentially, a TCP segment, okay, sits inside. So remember, we're coming, let me see. So you have, okay, so you have so I'm showing you here the datagram. So there's an IP, the network layer payload with the IP header. But what is the network layer payload? The network layer payload is the TCP segment with its own TCP payload with the TCP header. Okay, and typically the TCP header is about 20 bytes long, right? So this is the header size here, and the maximum segment size is there's some number. So usually, like for example, it might be 12. For example, here I said 1460 consecutive bytes. So that's a possible value of the maximum segment size. Okay, I'm also saying something about the IP packet. So IP packet, just like there's a maximum segment size here, there's a maximum transmission unit. For example, it could be 1500 bytes. So on Ethernet, it's 1500 bytes. It's configurable by the network administrator because it's the routers that have to enforce this. So when we talk about network layer, we'll see that sometimes, based on the value set by the ISP, meaning the maximum transmission unit, a packet might need to be broken up. Okay, and that function is called fragmentation and assembly. Okay, and that's something, but that's done by the network layer. We don't do this at the transport layer. Okay, so this is where the TCP segment fits into the protocol stack. So here you explicitly see the encapsulation. Okay, any questions so far? It's nothing too difficult here. Okay, sequence numbers. Okay, so as I said, we want to give a sequence number to all information I send. So I need to find a sequence number for the first byte, right? And now, because I'm going to acknowledge both sender and destination or receiver have to agree, right? They have to agree on the sequence numbers. So what's the naive thing to do? Or what's the obvious thing to do? Like, where should I start? Sorry? Where should I start? Yeah, you could, right? Yeah, 0, 1, 2, 3. Or if you don't like 0, 1, 2, 3. Right? Yeah, that sounds reasonable. Every connection, I start at 1. But it turns out we don't do that. Right? We don't. So, for example, let me just continue this here. So you have this. So just to say a little bit about the acknowledgement. So if the sender sequences, so suppose that there's 64 bytes here. Okay, so and suppose I use 1, right? So 1, 2, all the way up to what? What would the last byte be? What would the sequence number of the last byte be? A bit louder? Yeah, 64, right? Then this segment will get sent. At the receiver, I will receive them, and I will send an acknowledgement. Now, the interesting thing is what TCP does. I'm kind of spilling the beans here because later we'll try to figure out what TCP should do. But I'm telling you what TCP does is when it acknowledges, it's going to acknowledge what I'm expecting next. So what will the acknowledgement be from the sender to from the receiver down here to the sender? I said the ACK number is the next expected byte. So what will that be? Well, what's the next expected byte? It received the sender sent 1 through 64. The receiver received 1 through 64. Yeah, so it's going to send back to the sender 65. So in its acknowledgement will be the number 65. Okay, so that's kind of how this thing works. Okay, now the question is, okay, why? So what's your name? Spell it for me. Aslam. So Aslam suggested the obvious choice, is, which is 0, 1. It doesn't matter, but this may not be a good idea if every connection did that. And this is primarily because the network is best effort. So you could, for example, you start a connection, you start with 1, 2, 3, 4, 5, right? And suppose packet 5 gets delayed in the network. So TCP kicks in and resends packet 5, and that packet 5 for this flow, it completes the flow. But the old packet 5 is still flying around the network. Now, this same sender-destination pair starts a new connection. They start at 1, 2, 3, 4, 5. And now the old packet 5 comes in. There's no way to know, for the receiver to know, was this an old flow or a new flow? Right? So do you see the problem? Because of this, we don't want to start with a deterministic starting point. You want a random starting point. Okay? So that's what happens. So the ISN, which is initial sequence number, is a random quantity. Okay? And so what actually happens is the protocol provides for sort of defines a shift register. So one way of generating random I say quote unquote random because it's not really random, or pseudo random quantities is a shift register. So if you have a shift register sequence and you initialize the shift register to a certain initial set of values, this thing will generate a sequence of numbers that's predictable. It's the same reason why, for example, sometimes when you write code, you have a random seed, right? If you remember that random seed and then you feed it back to your code again, you can get the same sequence of random numbers, because most pseudo-random number generators use a shift register sequence. So TCP provides for that. It uses a very long shift register sequence. So the idea is that, like, I don't know if you ever thought about this, but anything a computer does will repeat. Did you ever think about that? Because a computer is nothing but a finite state machine, right? It cannot generate truly random things. So it's going to eventually, it will repeat. Okay, so this shift register sequence will repeat. But the repetition period depends on the initialization as well as the length, the number of shift registers. And the way they've designed this thing will wrap around so it's a 32-bit clock that ticks every 4 microseconds. Its period is 4.55 hours. So the idea is that this is long enough for any old flow to clear the network. It's kind of overkill, actually, right? But anyway, just to give you some facts about the shift register sequence that generates that random sequence. So this means that the sender generates a random sequence, but now the receiver needs to know that sequence. Correct? Now you can say, okay, maybe the receiver could know the shift register, but what about the initialization? You can't know it, right? So what happens is that the two hosts, the sender and destination, have to exchange sequence numbers. Now remember, the receiver is sending packets back to the destination. The destination is sending packets back to the sender. What are those packets? Do you know? What is the destination sending to the? Yeah, it's sending ACKs back, right? I mean, it might have its own data to send back, but if it doesn't, it's still sending ACKs back. So those ACKs are using TCP, and they're going to have sequence numbers and all that stuff. Okay? So the two hosts need to exchange sequence numbers. Okay? And the way that that's done is through a three-way handshake. So this three-way handshake sets up the connection, and as well as allows the two hosts, the sender and destination, to exchange sequence numbers. Okay, so this thing looks like this. So we'll do this and then we'll stop, okay? So here's the three-way handshake. There's a SYN packet, a SYN ACK, and an ACK. You remember? Oh, whoa, that was bad. Sorry. I hope there's an inner glass thing in there, right? Shit. All right. Sorry. So here's the three-way handshake: the SYN, ACK, and ACK. And I think when I did the Wireshark, we saw a SYN packet, right? Yeah. So it's this SYN packet. Okay. And then after the three-way handshake, you send data. So yeah, I think I have details on that. So this is the anatomy of the TCP packet, right? So now this is everything, okay? You have source destination port. You have sequence number. This is the sequencing for looking at, for checking things out of order and lost. You have the acknowledgement. You have a whole bunch of header flags. You have this advertised window field. This is for flow control. Okay, right here. This is for flow control. You have a checksum and a bunch of other flags, header fields, and then your payload. Okay. Now on the very first SYN packet, A is talking to B. So A is the source port, B is the destination port. And A puts its initial sequence number, and it sets the SYN flag in this field to on. So I know this is a SYN packet. In the response, remember B, the source and destination port are swapped. So now B is the source. So this is the acknowledgement from B to A, and B just sets the SYN ACK flags. Okay, and it puts its initial sequence number here. And its expectation is A's initial sequence plus 1. Right? So now it's telling A, here's what I expect from you next. That means, notice that that's an implicit acknowledgement that I got the first packet. Correct? Because I'm saying I'm expecting the next one. All right? And then C just responds. Okay? All right. So I'll just end with this. So this is something I'm sure everybody has experienced. If you haven't, I'm impressed. You're surfing the web. You click on a link. And then you just wait. Like maybe for a minute or two. Right? And then you get tired of waiting. So you click the link again. And then what happens? It goes through. So who's experienced this? Right? So I did this too. So I realized I found an explanation of what's going on. When you initially set up a connection, you have no idea about round trip time. So usually you set the round trip time to be very large. So when you send the initial SYN packet, that SYN packet, if it gets lost, of course the sender will never respond. I mean, the destination will never respond. And so you're just waiting. And so you click again, it resends the SYN packet. Okay, so you get what's going on, right? So you're essentially preempting the timeout, the TCP timeout. But the TCP timeout is intentionally set to very large because initially you don't know how long to wait. Of course, we'll see later that we're going to, in TCP, there's a mechanism for estimating the round trip time. So you do know how long to wait. So you can set your timeout more rationally. Okay, but initially you don't know. So I thought that was kind of cool. You can explain what's going on. When you're sitting there waiting, probably your SYN packet got lost, right? It has nothing to do with bandwidth or whatever. The initial connection was never made. Okay? Yeah, so I'm just explaining what's going on. Okay? And then eventually, to end the connection, you tear everything down. So remember, there's a SYN, SYN-ACK, ACK. There are a whole bunch of data and ACKs. And finally, to end the whole thing, you send a FIN, FIN-ACK. Because there's a two-way connection, so you have to end both FIN, FIN-ACK, and FIN and the ACK to this FIN. And this will tear down the connection and kind of release the port if you had a port and all that good stuff. Okay, so I think with that, we're sort of, so now what we've done is we've done a three-way handshake to set up the connection. And there's a whole bunch of data in between, and that's what we'll talk about next. What happens inside this part here? This data ACK and this ... This is where most of TCP lives, right? In ACKs and retransmissions and flow control and congestion control. All that lives in the middle there, and we'll talk about that when we come back on next Monday. Okay, thanks. Yeah, do you have a question?
Yeah, I don't really understand why they had to send feed twice. Because it's like, okay, I want to close the connection, then the other guy says, okay, you can close the connection. But
Yeah.
now I ask you, can you close the connection as well? Despite the fact that I know you wanted to close the connection.
Yeah, this is a good point. You saw me pause too, right? Yeah, I paused because I think the point is, anyway, if I have to guess, I think it's because you want to close the two-way connection because eventually I'm sending data and ACKs, right? So in some sense, there's two logical channels. You want to close them both, right? But I'll double check that. I mean, I think we can double check that by just looking in the TCP standard. Yeah, but this is a good question. You saw me pause too, right? I also was like, wait, why there two? Yeah? Yeah, it could be, yeah. Yeah, but then that goes on forever. Right? I mean, then how do you know I received the second ACK? And so on. It never ends. But I think it's to close down both directions. Okay, and any other questions? By the way, I want to remind you, you have homework 1, right? Homework 1 is about general networking. So please get on doing that. Okay, if I've uploaded 3 homework assignments, right? If you look at the handouts, there should be 3 assignments, right? Yes or no? It's there, right? Come. Yeah, there's question set 1, problem set 1, 2, 3. 1 is general, 2 is on, I think, transport layer, 3 is network layer. So these are the 3 problem sets. I think you can start doing problem set 1 already, right? It's the intro stuff. I want you to, what I would like you to do is to start with a clean sheet of paper or a clean Word file or whatever, and really think through each of the questions. The questions are not very hard. They're a bit open-ended. Okay? And actually, I think one of them is, why do we have MAC and IP addresses? So there are actually 3 questions that I really want you to think about that are very, very high level. One is, I already told you why we have MAC and IP addresses. The second is, why do we have reliability at link and transport layer? Okay? And the third is, why are there checksums at all 3 layers? These are questions that generally people don't ask. But these are the 3 of the many questions that bothered me when I learned about networking. And I think answering them helps you learn about networking and why decisions are made the way they are. Okay, so remember, so 1 we've already answered, why we have MAC and IP. And in case you want to start thinking about it, why do we have reliability at link and transport? And why is there a checksum at all 3 layers? Okay, I'll see you on Monday. Thanks.